So by God's grace, today we should be able to finish everything about binary operations so that we can move to another topic. So far, I'm just going to give a brief. We've been able to do some simple binary operation workings. We are on the properties now. We have treated closure. We have treated commutativity. And now we want to treat distributivity, associativity, identity, and then inverse. So those are the 4 things I think we need to work on now. Let me come again with the things we need to do. We have treated closure. We have treated commutativity. So now the 4 things that are left are associativity, distributivity, identity, and inverse. Okay, so with that in mind, we just quickly shift into action or swing into action. So for associativity has to do with relating just one binary operation. It has to be one binary operation. We want to do associative properties. We only talk about one binary operation. But if you are talking about distributivity, we talk about 2 different binary operations. So let me start with the associativity property. Associative property, from the word association, associative property. The property says that when you have a binary operation star and then you have this condition met for any variable A, B, and C, and then a binary operation star, okay, you can have this. So let's say we have this. Let me repeat that. Okay, let's say we have this. It must be equal to A star B, then all into brackets star C. Once we are able to, establish this condition for any binary operation star, then we say that the binary operation is associative. That is when we prove that it is associative. So I can give a very simple example to this. Let's say that when we have A star B, this is an example. If A star B is given as AB plus A plus B, this is associative. It's going to be a long explanation, but I just want you to follow keenly about how the arrangement is made. We want to now prove that this can occur. For the sake of sanity, I'm going to just use numbers, because if it is true for numbers, then we are just picking arbitrary numbers, ABC. So we can use real numbers to prove that. So what we need to do now is to say, okay, let me have A to be equal to 2. A is equal to 2. B can be equal to 3. I'm just using any arbitrary number. C can be equal to 1. So what I will just do is I want to prove for this now. Let me put it in a box that for any ABC, if this condition is satisfied, then I can say that I have a binary operation that is associative. So I will first prove the first part, which is the left-hand side part of the equation. So to now have A star B star C, A star B, and I need you to pay attention to something I'm going to be doing here. This A star B star C, don't rule of operation in mathematics follows BODMAS. So for BODMAS rule, we are going to first solve whatever it is in brackets. So B star C is what we are going to work with. And we are going to define our star, the binary operation, as AB plus A plus B. So it's going to be BC plus B plus C. So when you do that, you're going to have A star. Then open your bracket and use this definition. That will be 2 times 3. No, sorry. BC, that will be 3 times, yeah, I'm right. 3 times 1. That's our BC. 3 times 1 plus 3 plus 1. That's how to define it. And that A star, our A is 2, so we are not touching 2 yet. Let's just finish this. 3 times 1 is 3. 3 plus 3 is 6, and 6 plus 1 is 7. So everything we have here is going to give you 7. So A star 7. All right. Then we'll now work on this with A. So it's going to now be 2 times 7 plus 2 plus 7. In the order in which we have AB, then A plus B. And that's what we have here. So everything here will give us 14 plus 2 plus 7. That's 14 plus 7, 21. 21 plus 2 is 23. So our answer here will be 23. So if we have 23 for this, we will now check the other side. We want that this is for LHS, left hand side of the proof, is what gives us this left hand side. Now this is the left hand side. I'm writing it on top of it across the red box. Left hand side. This one will not be right hand side. So we will now check for this same 2, 3, and 1. We want to check whether in order we'll first operate A and B, then we'll now operate it and C. We'll see whether it will give us the same thing. If it is not the same thing, that means it is not associative. So the property of associativity is at the end of the day, you must get the same thing. So if you don't get the same thing, it means that that binary operation is not associative. So let me just bring to remembrance again. A is 2, B is 3, and C is 1. So I want to operate that A star, B star, C in the order of AB plus A plus B. So let's go. So I have now A star B. I want to operate this. Then bring it star C. So let's see. Our A is 2, so it's going to be 2 times 3 plus 2 plus 3, all in bracket, then star C. So 2 times 3 is 6. 6 plus 2 is 8. 8 plus 3, that will be 11. So I'll write 11 star C. And my C is 1. So I will just say 11 times 1 plus 11, then plus 1. That's what we get. So 11 times 1 is 11. 11 plus 11 is 20. Previous slide. What is the left hand side? What is the right hand side? So here in our previous slide, our left hand side gave us 23. And now our right hand side is also giving us 23. So our conclusion follows that, therefore, I want to write therefore in a normal mathematical language. Star is associative. That's the conclusion. Since left hand side is equal to right hand side, then we say star is associative. Star is a binary operation that is associative. So that's the possibility of associativity. Associative. Yeah. So that's the proof of associativity. And then it may not be associative, there's no crime, but I decided to use number because number is easy to work with than just using arbitrary value like ABC. It will give you unnecessarily long list of letters. So I will encourage you to practice it because we really can't tell. JAMB may not bring numbers, they may bring letters. So practice it with letters, we'll still get the same thing. Just for the sake of time and space is why I decided to use numbers so that our answers can be compressed. So it's fine that way. So another thing we want to talk is distributivity. Distributivity is not solely a property of numbers. It's actually a property of the binary operation itself. Yes, that's distributivity. And I'm going to explain it in a very simple terms. You are going to understand. So let me just say that if you have 3 plus, I'm already explaining distributivity. If you have 3 plus 5 times 2, if you have something like this plus is not distributive. That is, you cannot open the bracket with this plus. It is impossible to open bracket with this plus. But if you have something like 3 into bracket 5 plus 2, you can open the bracket because 3 into bracket means 3 times 5 plus 2. So I can do 3 times 5 plus 3 times 2, but I cannot do 3 plus 5 times 3 plus 2. I can't do that. So what the distributive property is saying is that not all binary operation can be distributed across values of another binary operation, just like normal number. It will be easier for us to show that the first one is not distributive, while the second one is actually distributive. So I'm going to present this binary operation in terms of what I've just explained in the next slide. Hold on a minute. So I want to just rush through everything. If you have a question, like I said last week, if you have a question, bring it. Let us look at your questions together, because that's the reason why I will tell you what we are going to be doing next class. So if you know what we'll be doing next class, you'll be able to go ahead, try and solve. If there's no question you can, if there's any question you cannot solve, you can bring it to class, then we'll look at it together. So it will be easy for you to overcome it. Okay. So I want to go to the next slide and explain distributivity. So for distributive distributive property, anyhow you want to call it, distributive property. Let me just use PPT. PPT for student of let me use TY. Student of chemistry will see PPT as precipitates, but I'm just using a shortened form for the sake of space. PPTY to mean property. Okay, so we say that in distributivity there must be 2 operations. There must be 2 operations. So this operation and this operation are binary operation. Then if you have A star B plus, I'm not using the normal plus C, and what you are able to get is A star B, this is close, plus A star C. Then we conclude that, sorry, I think my screen is not acting well, but I think I can manage it this way. So this binary operation star is distributing A across B and C. So A star B plus A star C. Let me just also cover the plus because it's also a binary operation. It's not an ordinary plus. It's not an ordinary plus. Just like I explained the other time, if I use 3, I just want to use an ordinary operation here. If I use 3 times 5 plus 2, this is the same thing as 3 times 7, and that's 21. But will it also be 3 times 5 plus 3 times 2? Let's check. If it is, 3 times 5 is 15. And when you add that to 3 times 2, which is 6, you will still get 21. So this proves that Multiplication is distributive over addition. I can use ordinary signs to prove that. But addition is not distributive over multiplication. The order can never, the reverse of this can never hold. It can never hold. So that is the law of distributivity. I'm not going to solve an example yet because of time. I want to make sure that today we end binary operation so that we can go to other topic. Then the next thing I want to talk about is the existence of identity. Existence of identity. For identity, identity is saying that there is always a particular element that when you operate it on another element, it will always return that element to you. And I'm going to give you two scenarios. Under multiplication, what is that one number that anything you multiply with it will always give you back your original value? I want to believe I have students in my class. Let me ask question. Shobayo.
1.
1. Good. That's
1.
nice. Yes, 1 is the correct answer. Anything you multiply by 1 will always return your answer back to you. That is what we call identity. So under multiplication, our identity is always 1. So in this binary operation, there will always be one particular element that any other element you operate on it will always return you the original value. So we call that element an identity element, and we always denote it by a letter E. This letter E is not unique. It's not unique because you can use any other letter as long as you identify it as an identity element. But under binary operation, mostly you will see the letter E being generally used as an identity. So if you multiply any number by it, you always get your number back. Okay? So let us try something. Let us try something. Is it possible we find an identity element for a binary operation that we used the other time? So just like you said, if I say 2 times 1, I will get 2. If I say 15 times 1, I will still get 15. So 1 is my identity element. Funny enough, even if you say 0 times 1, do you know you get 0 back? So that makes 1 a universal identity under multiplication. So anything you operate on 1, you always get you that number. So 1 is an identity. Can you think of a number that can represent identity under multiplication? What is it that you can add to any number and you get that your number back? Addition. Is there any number?
0.
Let me see. 0. Wow, I love that fast thinking. Yeah, 0. Anything you are adding to 0 gives you back your answer. Even 0 plus 0 will give you 0. Minus 10 plus 0, you still get minus 10. 1 million plus 0 is still going to be 1 million. So you have identity being 0. That's identity under addition. You can see that under different binary operation, or let me use normal mathematical operation. Basically, multiplication and addition, they have different identity. So identity under multiplication is quite different from identity under addition. All right? So please note that. So that is how you will generalize it to any binary operation. Every binary operation comes with its own unique identity. I come again. Every binary operation comes with its own unique identity. All right? So that's why I'm saying this identity is not a generic value. You have to show it. So I'm going to give an example here before I move to the last one. I hope I'm still being able to work with time here. I will have to delete this. Sorry, I'm taking away these ones. Okay, so let's talk about the previous example I gave. If A star B is equal to AB plus A plus B, if A star B is equal to AB plus A plus B, The question is find the identity element. Find the identity element. This is a binary operation. Find the identity element. Let me move away from the inactive part of the screen. Element. Okay. So this is a question. If this happens, we are looking for identity element. So this is how you are going to go by your solution. You will say let E be identity. We are looking for identity. So you can just use an A arbitrary element to get E, and then your answer must be A. This is the condition. For any element E to be an identity. For any element E to be an identity, any element you operate on E must return A for you. If 1 will be my identity, anything I multiply by 1 must give me that back, the number. So that's just the logic we are putting into this. So you are going to operate by this rule now. You have been given a rule. This is what will make you get the identity. I underline the rule. So I'm going back to it and I'm going to say my A star E is defined like this. AE plus A plus E. And when I do all of this, my answer must be A. That's the condition. AE plus A plus E. Wherever you see A, you put it. Wherever you see B, you replace it with the identity element. And at the end of the day, you must get your A back. So what do we do? What we are going to do is simple. Collect like terms. I can have AE plus E is equal to A minus A, because this A here has nothing to do. So I'm taking it to the other side, and then it's giving me this. So what I have next is I can factorize E out of here. I can factorize E from there. So I will have E into bracket A plus 1 is equal to 0. And you divide both sides by A plus 1, A plus 1. This cancels this. So your E is equal to 0. So the identity element under this operation star is 0. And this does not mean that it must always be 0. It just happened that in this case, the answer is 0. I can give you another question that you will not get 0. All right. So this settles everything you need to know for identity. And then I want to move again. I want to go to inverse. Inverse element. Existence of inverse element is a property of binary operation. So the existence of inverse element is given in this format. Just quickly rush it. So if my one is E, then I'm looking for, all right, so I'm looking for something that when I multiply by 5, I will get this identity element. So I can say 5 times, let me call it A inverse. A inverse, that is inverse element, that must give me identity. That's the rule for inverse. To get inverse, look for anything that you can multiply by an element and you get your identity. So in this case, if you look very well, the only number I can multiply by 5 to give me 1 is 1 over 5. So 1 over 5 now becomes my inverse, and 1 is my identity. All right, so I'm still going to erase this and then state the rule, because there must always be a rule. So an inverse is an element that when you operate it on another element, you will get the identity. So I can say A operated by any binary operation on A inverse must give you E, where you know that E is identity, then A inverse becomes the inverse element. This is how we state it. So let me just wrap this up with a nice box. All right. So it's fine that way. Okay. So having seen this now, I'm going to be using a very simple table to demonstrate everything you have here. I'm going to be using a very simple table to demonstrate everything you have here. Okay. I hope I have the luxury of time. Here I'm using a binary operation star, which is non-generic P, Q, R, S. Then I have P, Q. I can use, it's the same element I'm using across board. So let me just use, okay. P is here, Q is here. So this is P, Q, this is R, and this is S. Because JAMB likes tabular questions a lot. All right. So here you have um, you have P, you have P here, you have Q here, you have R here, you have S here, you have Q here, you have R here, you have S here, then you have P here, then you have R here, you have S here, you have P here, and then you have Q here, and then here you have S, you have P, then you have Q, and then you have R. All right, this is what you have. Now, based on this tabular property, there are only two questions that will be asked. They will ask you, number one, find the identity element. Then number two, find the inverse of a particular element. So if you are looking at this table, which of them do you think is the identity element? Based on the previous example that we have solved, what do you think the identity element is? Okay, is it still only Eniola that we have here? What do you think the identity element is? Identity element is anything you operate. Let's do it this way. So I'm going to give you something like this. Since you know that identity element is when you operate it on any element, you get your answers back. What do you think I can operate on P according to this binary operation? Let me put a dash here. That at the end of the day, what I'll get back is P. If you look through the table, or what do you think I can operate on Q? Because for this table now, the identity element can only be one particular element. I'm operating it on Q, and what I get back is my Q. I've given, if you look at that table very well, you will see one of those letters. So I need someone to respond to that. Let me wait a bit until you are able to digest it. Just check the table. I think it's only Eniola that is stable here. Eniola, can you unmute? Okay, so if you can't unmute, just follow through. I know that from what I can see, P times P will give me Q. P times Q will give me R. P times R will give me S. But P times X is returning P for me. Let me be sure that you know it's P I wrote here. I'm going to rewrite it more clearly. All right, it looks nice now. So P operated on S is returning P to me. The same way Q operated on S is returning Q to me. So from what I can see, R operated on S is returning R, the last column. Then S operated on S is also returning S. So from look of things, any element that I operate on S will always return that element to me. So it shows clearly that actually The only identity element that I have on this table is S. That's the identity element. Identity element is S. Identity element is S. And in the same vein, we can find the inverse of P. What do you think? Which element can I operate on P that will give me the identity element? You can see the condition in the red box up there. The condition in the red box is look for an element, operate it on another element, then you get an identity element. Now that we have been able to identify our identity element as S, what do you think will be the inverse of P? Inverse of P would be the element that I operate P on, and I'll be able to get S. From the table, I can see that if I operate P on P, I will not get S, I will get Q. So P is not the inverse of P. If I operate P on Q, I will not get S, I will not get the identity. What I'll get, inverse. So what this means is that when you operate P on R, you will get the identity S, which means R is the inverse of P. R is the inverse of P. That is why when you operate P on R, you will get the identity S. Let's go for Q. What are we going to do to get the identity? If you operate Q on Q, you get S. So Q is the inverse of Q. This just so happens to be that. Q is the inverse of Q, and then P is the inverse of R. All right? P is the inverse of R. So just like that, we have been able to establish everything that we have to do with binary operations. So I want to believe on this note, I've been able to cover everything binary operations. So if you have questions, you are free to ask. If you have questions, you are free to ask. You have your jam pass questions. I will really strongly advise that you go through them. Let me see if you can hold on a second. I think I still have a few minutes. I can quickly scout if I'm able to get a question that I can just quickly project here to make use of. Let me see how that can be fast. I can easily quickly scout for one that can be of help to us. Okay. Okay. All right. I want to look through a list of questions here. Okay. Just still hanging a second. The reason why most of these questions are not used in an online class is because they are not arranged in topical format. So, and to be able to arrange them in topical format is a whole lot of work. So one has to just, I think I saw a question here beautifully. All right. This is question 23. What year is this? Let me just check the year. So you can check out 2011 JAMB. Past question number 23. 2011 JAMB. All right, 2011 JAMB. Boys, this one is more direct in a way. I'm going to project it on the screen. Possibly if you can just try it. So I'm taking down this sharing. If you want to see more of this, because I'm not saving it, let me see what I can do. Maybe I can just quickly save, but then for the sake of bringing it back, I want to stop projecting. All right, so that I can share my screen. You will see the question. I think we have just 1 minute left. So please quickly just screen grab it and go and work on it before our time got used up. This is the question. Question 23 here. So you just go and work on this. You will get an answer. Please make sure you can submit the answer to me. Of course, you can work on this. Find the value of this. It's more direct. You are just going to arrange it. You put x where you put 3 where you see x, and then you put -2/3 where you see y. This is more of a direct question here that you can make use of. Quickly screen grab. Maybe in the course of scouting for other questions, time may just go, and that will be the end of the class. But I encourage you to always try and look for more questions to solve on your own. These are past questions in JAMB that you can lay your hands on and work on. For those who are interested in what the answer to that question may be, question number 23, you should get your answer in B, answer B. Let me see around 20 something if I can see another question like that. Okay. Okay, this is another one. I think this is, yeah, I love this. This is associativity, but it's more or less like they are not even asking you to test associativity. And of course, you can see two binary operation question comes together in this particular year, number 21 and 22. This is a binary operation. If the identity element is 2, find the inverse of 5. I love this. You can quickly screen grab 2 and work on it. Possibly next class, we can just use this as a revision question. What year is this? I need someone to note this for me because I'm not going to note it. This is 2012, 21 and 22. 2012 question 21 and 22. You can screenshot and keep it and